magnetic waves. Whereas Ez was set equal to 0 in the case of TE waves. Ez means direction of electric field in the, electric field component in the direction of propagation. And in TM waves, the component of magnetic field, that is Hz, in the direction of propagation Z is 0. Then you get another group of waves known as transverse magnetic waves. So magnetic field is entirely transverse to the direction of propagation. That is why the name transverse magnetic waves. So which is the direction of propagation? Z. So Hz is 0 in the Z direction. That means H component can be present in the X or Y direction. Okay. So Hz is equal to 0, and we had obtained that when you give Hz equal to 0, Hx equal to 0 and Ey equal to 0. But Ez is not equal to 0, Ex is not equal to 0, Hy is also not equal to 0. That means these three components exist. Which one? Ez, Ex and Hy will exist, whereas Hz, Hx and Ey will not exist. Okay, just compare and contrast with the TE waves. In that case, it was just the opposite. Okay, so moving in the same process as in TE waves, you always write the expression for wave equation. Then you get dou square Hy by, instead of E, you have to take magnetic field H. That's only difference. You say, follow the same procedure. So writing the wave equation, dou square Hy, where did we get this? You can just go back and see how we started with transverse electric wave. Same procedure. So I'm not writing everything again. I simply start with the step of dou square Hy by dou x square plus gamma square Hy is equal to minus omega square mu epsilon Hy. This is where do we get this wave equation, which we have obtained earlier, wave equation. Okay, so that is, you can write dou square Hy is equal to, you taking this gamma square to the right hand side and adding with omega square mu epsilon, you write it as minus h square, small h square Hy, where h square is equal to gamma square plus omega square mu epsilon. Okay, same representation here also. So instead of Vy, we start with Hy. That's only difference. And procedure, the remaining procedure is also the same. So following the same procedure as that for TE waves, the solution for Hy in the same way as we proceeded for TE waves, that is considering it as a simple harmonic motion, we can write the solution for the second order equation as Hy is equal to C3 sin Hx plus C4 cos Hx e raised to minus gamma Z. C3 and C4 are the new constants here. For TE, we took them as C1 and C2. So here we take two different constants, C3 and C4. What is H? H is equal to, H is given by H square is equal to gamma square plus omega square mu epsilon. See, this is the equation. From here only we got the solution for Hy in the next slide. See, so we get the general solution for simple harmonic motion in terms of C3, C4 constants and sin Hx and cos Hx multiplied by the phasor term e raised to minus gamma Z. Now, we cannot apply boundary conditions directly here. In the earlier case, we could have applied directly E because we are getting Ey, which is equal to 0 at x equal to 0 and x equal to A. But here we cannot do that because we know that Hy is not 0 because tangential component of H is not defined here. It is that is not our boundary condition. So we cannot directly apply boundary conditions to evaluate C3 and C4. നേരത്തെ നമ്മൾ അതാ ചെയ്തത്. നേരെ അടുത്ത സ്റ്റെപ്പ് എന്ന് പറഞ്ഞാൽ ബൗണ്ടറി കണ്ടീഷൻ Ey അപ്ലൈ ചെയ്യുകയാണ് ചെയ്തത്. സ്ലൈഡ്സ് നോക്കിയാൽ മതി. Okay, but here we cannot apply them directly as H tan is not equal to 0 at the surface. That is not our boundary condition. As the tangential component of magnetic field is not equal to 0, we cannot directly apply the boundary condition. So what should we do? So, but from equation G നേരത്തെ നമുക്ക് കിട്ടിയിട്ടുണ്ട്. G ഏതാണെന്ന് നോക്കാം. We'll go back to those slides. Here we have G. These are the equations G. Okay, G you have here. You get, earlier you have got set of equations C. Here you have 3 equations. But here, in this case, gamma Ey is equal to minus j omega mu hx. Then you have minus gamma Ex minus dou Ez by dou x. In that, Ez is already 0, equal to minus j omega mu hy. Then you have the third equation, dou Ey by dou x equal to minus j omega mu hz. ഇതൊക്കെ എവിടെ നിന്നാണ് കിട്ടിയത്? അത് ഓർമ്മയുണ്ടല്ലോ അല്ലേ? നമ്മൾ അന്ന് ആദ്യം ആ കേൾ ഇക്വേഷൻസിന് എക്സ് വൈ സെഡ് കോമ്പണൻസിനെ സെപ്പറേറ്റ് ചെയ്ത് എഴുതിയതാണ് ഇതെല്ലാം. ഓക്കെ, ഡിറ്റർമിനന്റ് ഡെൽ ക്രോസ് കേൾ ഇക്വേഷൻ, ഡെൽ ക്രോസ് ഫോമിൽ നിന്ന് 3 കോമ്പണൻസ് സെപ്പറേറ്റ് ചെയ്ത് എഴുതിയ ഇക്വേഷൻസ് ആണ് ഇതൊക്കെ. ഓക്കെ, ഇതൊക്കെ നമുക്ക് നേരത്തെ കിട്ടിയിട്ടുണ്ട്. അപ്പോൾ അത് അവിടെ നോക്കുക. സോ ഫ്രം ഇക്വേഷൻ ഡി, look at the third equation. You have dou Ey by dou x is equal to minus j omega mu hz. Okay, so can we take this equation? Let us see, because we already have formed an expression for hz. Hz we have. So taking that third equation, that is from G, you take that third equation. You write that third equation here. This is that third equation. J omega, sorry, not the third equation. It's the third equation. Let me see once again. Okay. This was the actually it was, there was another set of equation along with this. I think I should have written it here. So that or I will write those equations. Along with them, you have the H components also. I forgot to write it here. Okay, so you have a third set of equations also named as G. That is from where we get correspondingly. I think these are the set of equations. Okay, so those new along with them you have dou Ey by dou x is equal to minus j omega mu hz. Okay, no need. Okay, I think this will do. J omega mu hz. Or j omega epsilon Ez, which was that. Okay. So, that is, let me write it here. That is gamma hy is equal to j omega epsilon Ex minus gamma hx minus dou hz by dou x. ഇത് ഞാൻ എഴുതിയില്ലായിരുന്നു, ഇത് അവിടെ തന്നെ ഉള്ളതാണ്. നമ്മൾ ഇത് മാത്രം എഴുതി പോയതുകൊണ്ട് അത് ഞാൻ അവിടെ അന്നേരം എഴുതാൻ വിട്ടുപോയി. ഓക്കെ, വിൽ റൈറ്റ് ഇറ്റ് ദെയർ. സോ എച്ച് വൈ, അതായത് എച്ച് മറ്റേ രണ്ടാമത്തെ കേൾ ഇക്വേഷൻ എടുക്കുമ്പോൾ ഇതും കിട്ടുന്നുണ്ട് അതിൻ്റെ ഒപ്പം തന്നെ. 2 കേൾ ഇക്വേഷൻ, ഞാൻ ഒരെണ്ണത്തിന്റെ മാത്രമേ അവിടെ എഴുതിയിട്ടുള്ളൂ. ഓക്കെ, ലെറ്റ് us take. So this equation, this third equation, this we have to consider, not this one. So this third equation, this set of equations you get from del cross H. Okay, so this from del cross E. അങ്ങനെയാണ് കിട്ടിയത്. ഇതും അതിൻ്റെ ഒപ്പം വരുന്നതാണ് മറ്റേ കേൾ സെറ്റ് ഓഫ് കേൾ ഇക്വേഷൻസ്. യു ഹാവ് ടു റൈറ്റ് ദം ബിക്കോസ് ഫോർ ടി ഇക്വേഷൻസ് വി നീഡ് ഓൺലി ദ ഫസ്റ്റ് സെറ്റ്. ദാറ്റ് ഇസ് വൈ. സോ ഐ വിൽ റൈറ്റ് ദോസ് ഇക്വേഷൻസ് ഓൾസോ ദെയർ. ഫ്രം ദിസ് യു ഗെറ്റ് ഫ്രം del cross H is equal to J plus dou D by dou T. അതിൽ നിന്ന് കിട്ടിയതാണിത്. J is equal to 0 as sigma equal to 0. ഓക്കെ, അതിൽ നിന്ന് കിട്ടിയതാണ് ഈ 3 ഇക്വേഷൻസ്. അതിൽ നിന്ന് ആ മൂന്നാമത്തെ ഇക്വേഷൻ dou Hy by dou x is equal to j omega epsilon Ez. അതെടുക്കുന്നു. യു ടേക്ക് ദാറ്റ് ഈക്വേഷൻ. എവിടെ? ഓക്കെ, if you take from G j omega epsilon Ez equal to dou hy by dou x. Okay, you take that. G avada ഞാൻ മാർക്ക് ചെയ്യട്ടെ, അല്ലെങ്കിൽ നിങ്ങൾക്ക് കൺഫ്യൂഷൻ വരണ്ട. ഇതാണ് G, set of equations marked as G. These are the set of equations G. Okay. So taking that third equation from G, here you get j omega epsilon Ez is equal to dou hy by dou x. Hy we already have an equation, isn't it? Here, hy we have written an equation. Here, you take it, C3 and C4, in terms of C3 and C4. So you find out dou hy by dou x, and Ez will be h by, you find out dou hy by dou x, that means, what do you get? C3, h into C3 cos hx plus C4 cos h into C4 sin hx into e raised to minus gamma z. Okay, so you take that component, so that you will get, when you perform that dou by dou x, you will get h by j omega epsilon into C3 cos hx minus C4 sin hx into e raised to minus gamma z. You get Ez. Now, for Ez, you can apply the boundary conditions, because Ez is equal to 0 at x equal to 0, and Ez equal to 0 at x equal to a. 0 and a are our boundary limits. Okay, you know the heights at which the parallel plates are placed. So first you give x equal to 0, that means you will get C3 equal to 0. Okay, and when Ez is equal to 0 at x equal to a, you give it here. Again, similarly, you get h is equal to m pi by a. Okay, and C4 is equal to 0, and C4 is present, C3 is 0, and you also get h is equal to m pi by a. That's similar to what we got earlier for TE waves. That means, in general, we can write the amplitude component alone as Ez dash is equal to minus m pi by j omega epsilon a into C4. ഇത് എവിടെ നിന്നാണ് കിട്ടുന്നത്? ഇതിൽ നിന്ന്. C3 0 ആയല്ലോ, അപ്പോൾ ബാക്കിയുള്ളത് എടുത്താൽ മതി. Ez dash is equal to h by j omega epsilon into C4 sin hx e raised to minus gamma z. ആംപ്ലിറ്റ്യൂഡ് മാത്രം എടുക്കുകയാണെങ്കിൽ അങ്ങനെ എഴുതിയതാണ് ഇത്, വേർ h is equal to m pi by a, അത് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്തു. So similarly you get hy will be, hy dash will be C4 cos m pi by ax. ഇത് നമുക്ക് ഓൾറെഡി അത് അറിയാം. hyയുടെ ഇക്വേഷൻ ഇത്, C3 0 ആകുമ്പോൾ ഇത് ബാക്കിയുള്ളത് എടുത്താൽ മതി. അപ്പൊ ഏതൊക്കെ കിട്ടി? Ez കിട്ടി, hy കിട്ടി, then ex കിട്ടി. ex നമുക്ക് ആദ്യത്തെ ഇക്വേഷനിൽ നിന്ന് കിട്ടും. 3 ഇക്വേഷൻസ് എഴുതിയില്ലേ, G ഇക്വേഷൻസ്, അതിൽ നിന്ന് ex കണ്ടുപിടിക്കാവുന്നതാണ്. ex is equal to ഇതാണ്, ഇതെവിടെ നിന്നാണ് കിട്ടുന്നത്? ഈ മൂന്നാമത്തെ ex dash, അതായത് ഫ്രം, അതിവിടെ എഴുതാം, G. Which one? Which equation from G? Which equation you have to take? Gamma hy equal to j omega epsilon ex. From that equation, you get ex dash also. So why that dash has been added? To indicate the phasor amplitude component alone. You can write the complete equation by adding e raised to minus gamma z term also. So from that you get ex dash. Ex dash is equal to gamma hy by j omega epsilon. So gamma hy means C4 cos m pi by ax. That is how you get the third equation. So now we get the 3 components. That means we write the complete TM waves in terms of e raised to minus gamma z also as Ez is equal to j m pi by omega epsilon a into C4 sin m pi by ax. We put a bracket here. Into e raised to minus gamma z. Ex is equal to gamma by j omega epsilon C4. Just add that this propagation constant term e raised to minus gamma z term to Ez dash, ex dash and hy dash. So you get the complete Tm waves, which we can write as the set of equations named as H. Okay, so now we get the expressions for Ez, Ex and Hy. These are the set of equations for Tm waves. You will be asked to derive the equations for either TE waves or Tm waves. Okay, these are the equations for Tm waves. Or the waves to be similarly propagating, gamma should be equal to j beta, that is alpha equal to 0, which means you have to simply replace gamma by j beta. Then you will be getting the equation similar to what we got in TE waves, propagating Tm waves. So which are the components in Tm waves? Ez, Hx and Hy. All the other three components are 0. Okay. So now we have the equations for Tm waves also, similar to TE waves. Now, in this case, as before, if we put m equal to 0, what happens? നേരത്തെ നമ്മൾ m equal to 0 TE വേവ്സിൽ കൊടുത്തു കഴിഞ്ഞപ്പോൾ എല്ലാ കോമ്പണൻസ് 0 ആയി പോകുന്നുണ്ട്. അത് പക്ഷേ അപ്പോൾ അത് അലൗഡ് അല്ല. ബട്ട് ഇൻ ദിസ് കേസ് വാട്ട് ഹാപ്പൻസ് ഇഫ് വി ഗിവ് m equal to 0? For Ez, it becomes 0. Then what about Ex? If you give m equal to 0, does it become 0? No, because cos of 0 is 1. It doesn't become 0. Then Hy, there also cos of 0. It doesn't become 0. That means Ex and Hy will still be present even if m equal to 0. That is, for Tm waves, you can observe a very important property, that even if that mode where m equal to 0 is chosen, all the three fields do not become 0 simultaneously. Only Ez will become 0. Ex and Hy will still be present. That means electric and magnetic fields are still present. That means m equal to 0 is possible in the case of Tm waves, which we treat as a special case known as transverse electromagnetic waves, because here Ez becomes 0 and Hz is already 0 for a Tm wave. That means both the electric and magnetic fields components in the Z direction are becoming 0. So such a case we call as the transverse electromagnetic waves, a special case of Tm waves actually, not for TE waves, only for Tm waves. When m equal to 0, you get the special case of waves known as transverse electromagnetic waves, where both electric and magnetic field components are 0 in the direction of propagation, or we call them as transverse electromagnetic waves. For such transverse electromagnetic waves, we can write the set of equations also. So these are known as TEM waves. So what are TEM waves? They are the case where Ez equal to 0. It's a special case of Tm waves. Ez is equal to 0 and Hz is equal to 0. Okay. So it's a special case of which one? Tm waves. Special case of Tm waves. Okay. Where both electric field and magnetic field components are 0 in the direction of propagation. You also call it as the principal wave. Tm wave is also known as the principal wave. Okay. So you will be asked in some cases to define what is meant by a TEM wave or a principal wave. This is what. Okay. So that is it for Tm waves and TE waves. Now, we have seen the basic equations for Tm and TE waves. So I think we can stop here today. Enough